everybody. Thank you to be here. I know it's Saturday, it's the last talk of the day. My name is Alessandro Confetti. I am lead technologist at ThoughtWorks Italia. And today, I would like to talk about this weird title I entered, because it's full of buzzwords and strange names. And another speaker told me that his own personal buzzword index is too high on this title. But again, I would like to know from you, if anybody of you do know about IPFS? How many? Oh, good. And Ethereum? Lot of. Good. EmbarkJS? No, what? Just one. OK. So, interesting. Before going to code and seeing a small demo, I would like to talk about my very own personal timeline of the internet as has been built so far. So we started with a very decentralized system, was ARPANET. The building blocks of the internet were built very long time ago, and they helped build the first static World Wide Web revolution in 1990. So we have HTTP and HTML based on TCP and DNS thing, and it took almost 3 years to figure out how to trigger some scripts on the server through HTTP. Thanks to CGI. I don't know how many of you have seen CGI in your life, but it was a very ancient technology. And by the same time, around 1993 and 1995, also another key component of the first dynamic World Wide Web was born, MySQL, which was the internet database at the moment in order to build dynamic things in PHP and other languages, so on. And another very interesting key point of the evolution was almost 10 years later. Of course, CGI systems were very simple systems, and in 10 years of internet, system got very complicated. Deploying a web server was not enough. You have to do a lot of other services together, place them, configure them, scale them in order to fulfill the growing demand. And so Amazon has a very interesting idea. Others tried before, but the very first successful service built this way was built by AWS in 2004 and was a queue services. The idea was to build an infrastructure and offer it as a service in order to let companies build on top of very complex technology in an easy way, and don't bother about scaling up or down based on demand. But at that time, the internet was still too much synchronous. Scaling, horizontal scaling and vertical scaling was really an issue. And in my personal timeline, of course, I think that 2009, late 2009 or early 2010, was the moment where something happened, and asynchronous services, non-blocking I/O, actor models became to be a popular thing, a well-known thing. Again, the technology behind them were not so new. The actor system has been around for almost 20 years before. But again, nobody could not be asynchronous since then. In some way, all the other systems needed to upgrade in some way or another. And so much more richer, much more complex systems, again, were built. And in 2014, another very interesting service from AWS was born, AWS Lambda. So you don't need to bother about services. You just build functions, and you can run them on very complex, very big systems without any effort. So from Elastic Service, we moved to Elastic Function Computing. Incredible. But in this way, we moved from a decentralized ARPANET internet, as you would like to say, to a worldwide centralized serverless computing. So when we are talking about today about serverless computing, we are talking about a bunch of big companies, AWS, Google, Microsoft, IBM, Oracle nowadays. They are struggling to compete in this market. So, of course, inside AWS, there is a very complex distributed system. But it seems that nowadays we are happy in building big silos of data for customer. Think about Google, think about Facebook and Gmail and other things like this. And also big silos for computing resources. So we delegate everything to those big giants. And it's useful. It's useful. We can build very interesting things with them. But there is a but. There is another way of seeing such a thing. And when you talk about centralized thing, I think you could easily find out this image, which actually is from 1964. And there are plenty of articles with such an image describing the difference between centralized, decentralized, and distributed networks. But again, the image is quite old. And I think that I rather prefer this one in order to start a discussion about which kind of different system we can build. And of course, talking about distributed, decentralized, and peer-to-peer, which is the new guy on the block, new kid on the block, is a bit complex nowadays. Yes, of course, centralized systems are easy to explain. All the clients connect to a central server. Distributed systems get a little bit trickier to describe. Yes, you can have distributed and decentralized system. You can have distributed and peer-to-peer system. And the real question is, who owns the network? I would like to advise you to read these two blog posts from which I took these images. And talking about who owns the network, for example, let us identify peer-to-peer hybrid system or pure system. And pure system can be with a facilitator or without. Just to give you an example, Skype, Spotify are peer-to-peer networks. They are fully decentralized, but they are hybrid. You have gates, you have central gates you have to pass through for authentication and other things. So there is a central point that can be switched on and off in order to let you enter or let you inside the network. Bitcoin, for example, is a full, pure peer-to-peer network. Ethereum, we can argue. It's of course, I think it's a pure peer-to-peer network with a facilitator, because the Ethereum Foundation can force an hard fork, for example, and so change the rules, in some way changing the rules of the peer-to-peer network. So it's a strange beast. But again, we live in a complex world. The idea is that if we are able to build real peer-to-peer networks and build on top of this both services and also computing power, we can build very interesting things, and perhaps also deal with things like democracy and distribution of resources and other things as well, resilience and so on. And if I have to describe you another timeline about those efforts, yes, we can start with Usenet in 1979. It was the very first self-organized decentralized service. It was so self-organized and decentralized that worked also in disconnected networks. Before having a full internet connection between Australia and the USA, they used to ship tapes with all the news inside the Usenet servers in the US to Australia, load them in a server in Australia, and spread across the country. So it could work also in disconnected network as well. And it's still in use today for different reasons of the origin. Not all they are legal at the moment. But again, and the second milestone was Napster. Napster proved that peer-to-peer technology could be delivered across the globe, across the internet, even if the bandwidth was very low. I don't know how many of you can remember how slow was the internet in 1999. It lasted only 2 years because it was an hybrid system, so they easily shut it down. But other systems emerged, BitTorrent, and you can name a lot of them. And then there is Bitcoin. We can say a lot of things about Bitcoin, and it's hard to describe it because it combined a lot of technology that were already been proven before or developed before, but it was able, Satoshi Nakamoto, to build them in a way in order to make a real functioning, trustless, pure peer-to-peer payment services. Yes, of course, we can talk about blockchain, we can talk about cryptography, we can talk about cryptocurrencies and a lot of things. But it was the very first time that all those things could work together. And on top of Bitcoin, other things, other services emerged in order to replace, for example, DNS or authentications like Namecoin. Of course, we can argue about how much successful they were or are nowadays, but again, was an important milestone. And then a brand new bunch of peer-to-peer technology able to spread across the globe data in a very efficient way were born in 2013, and late 2013 and early 2014, DAT and IPFS. We will talk about IPFS today, but I strongly suggest you to take a look also at DAT, which enables, for example, data synchronization between nodes in an easy way. And then, to go in parallel with the other timeline I presented you before, we need to talk about Ethereum. Ethereum, again, used the ideas and technologies present in Bitcoin to develop a new stack inspired by blockchain 2.0 ideas in order to enable smart contracts. But what are smart contracts? Are functions executed in a very complex environment. So it seems to be a very similar idea to AWS Lambda. You have function, you run inside a virtual machine in this case. We can talk about this later, but I have seen that most of you know what Ethereum is, so we can go fast in this case. And strange enough, even in such a distributed world, a new interest in database, in distributed database, in blockchain database emerged nowadays. One is BigChainDB, there is FaunaDB, there are other initiatives. And the idea is that we have a lot of public data we need to store, and we need to be able to share across the globe, avoiding censorship or companies or other things. We need a lot of public data. So, from the Usenet, from very far ago, we are now in a world when we can also try out peer-to-peer computing. Again, I don't think that we can say that Ethereum can compete with AWS Lambda nowadays for an enterprise. But it's a really interesting starting point, and we need to look at it. So let's go back to 1990. Easy time. You want to build a website, you just need a client, a web server, some storage, and you go. Of course, things got complicated also those days, and if you want to scale up, you needed to add perhaps a load balancer very long time ago. But as you may guess from the orange lines, one request for a file, even if you have two web servers, is answered just from one of them. And things can only get worse. I mean, if you need a proxy because you need to zoning to distribute your web server across the globe in order to meet the demand, after all, the complexity of the infrastructure you are building, again, just one web server responds to the request. A single request, a single response. So, for example, what does it mean to build a website on top of IPFS? What's the difference? First of all, the IPFS network is a peer-to-peer network, a pure peer-to-peer network. So the nodes of the network are worldwide, and they can talk with each other. And if you want to place an HTTP call, you call an HTTP IPFS gateway, which is a server, which actually is a node of the network, that can translate between the HTTP protocol and the IPFS protocol. And the interesting thing is that once the request has been sent, the network responds in a peer-to-peer way. So they are not giving back to the gateway a file, choosing which is the nearest node here in order to get back a file. They send back to the gateway a bunch of blocks, because the storage inside each node is done like this. So you have a storage in which you have files that are not really files but objects in a Merkle tree. And each file is split across in multiple blocks. So when the network needs to respond, sorry, I can use this, needs to respond to a request, you can fetch blocks from multiple nodes. And this is a key feature of every peer-to-peer network, because it enables you to fetch information with very low bandwidth, asking very low bandwidth to each node. So even nodes that are not on a high bandwidth side can respond to the request and provide just a small information, as many of you who use BitTorrent-like system knows. Of course, there is a bottleneck here, because then from the HTTP IPFS gateway, there is only one response. So it's very fast loading things from the HTTP gateway, but again, there is one server responding to the client. This, of course, is improving because you have also the IPFS protocol. So if from your client you ask for a file through the IPFS protocol, and we are having also implementation in the browser for this. They are not quite ready, but I think they are worth a look. Then, in this case, every node responds to the client. So you have no bottleneck. So if this seems too complex, I mean, why we need such an environment if we have S3, for example, from Amazon? Yes, of course, you have S3. There are multiple needs in this case we can discuss now. So what does it mean to install IPFS for the ones who don't know it? So you just download the IPFS node, extract it, place the binary somewhere, do an IPFS init, which means it creates a local repository inside your home folder, and then you can start up the IPFS daemon and access the local web guy. So let's try to do it. So I already done an APF init before. Let me increase the size. I think it's too much small. Okay. Okay. So first of all, as you can see, starting a local daemon. So this is on my very own machine. So starting a daemon here also start a gateway. So each node of the network can be a gateway as well. So in this case, it's very easy to move from a gateway to another. And then there is another important feature we are going to discuss, which is content-addressed access to files. So now we have started the daemon, and we have a nice local interface that can show us some information. For example, the peer ID, which is an hash identifying this peer node, on which network addresses has been published this service, and we can look for connection around the globe. So we can see that now my daemon is connecting to those guys around the world. Okay? So, and the longer we let the daemon run, the more connection we can get, and so on. We also have a very simple file browser, and we have two files here. We can see the first strange thing. So we don't have file names here. We have an hash. And I will go to this very quickly. In this case, let me say that those two strange files are actually the application we are seeing now. So even the local application we are seeing here is a peer-to-peer distributed application. So it's a JavaScript application, you can see. quite common. And it's published in this way. Because what does it mean to publish something inside IPFS network? Let's try to do it. So let's say that we have, sorry. OK. Let's say that we have a very complex HTML application, like this. OK? So let's try to run it on IPFS. In order to run on IPFS this thing, so we have just one file. The very basic thing we can do is add this file to the local repository of IPFS. So we can say IPFS add index. And what IPFS, are you able to see the screen? Perhaps it's better to make it bigger. OK? So there is this strange thing here. So when I say add index, IPFS says to me, OK, I added index HTML, and for me is named in this way. This is an hash identifying in a unique way across all the peer-to-peer network my file. And of course, if someone else has my own very idea of building such a complex web page with the exact content, they will have the same hash. So let's try to use an the HTTP IPFS gateway. Sorry, I don't know if you are able to see up there. So we are accessing now my local gateway. OK? This is the daemon So we can take this hash and say this. And we got the file. OK, a very complex word for a very easy task. But now, if I take the same hash and go, for example, to the default HTTP IPFS gateway, which is maintained by the company who made IPFS. So this address here, https ipfs.io. OK, and I paste the same content, I'm able to see it again. So my content has been published through the peer-to-peer network to all the peers. I mean, there is a cache. We need to discuss about the cache in IPFS. But let's say, for the sake of simplicity, that now my content is available on the peer-to-peer network. And even if I shut down my daemon, for a certain amount of time, my content could be available. OK. Let's do another bit more complex work. So let's say that this application is not complex enough. We want to build a more complex application with an index and a link. So we want to access also another file. Now, instead of publishing each file once at a time, we can tell IPFS to say, just add the whole folder. And now something new happens. So we have, again, index, the new file talk, each one with their own hash. But we also have an hash for the folder. And that's a very interesting feature based on Merkle trees. Merkle trees are structure in which you build a tree. Each leaf of the tree has an hash. And each parent of the leaf has an hash computed upon the hashes of their leaves. So if something changes inside one of the leaf, also the corresponding parent hashes change. So in this case, we can do two things. We can try, given the fact that the HTTP IPFS gateway is a bit smart, so it behaves like a web server. If I ask for the root, it searches for an index file inside and display it. So we can ask for the folder. And we have the new file. Now, let's click on the link. And as you can see, another interesting thing happened. So the URL up there has an hash and then the name. So all the children of the parent folder, the root folder, are addressed by name. It means that if I get the folder on another node, and in IPFS language, I pin it, so I say, I want this folder to stay permanently on this node, I can assure that nothing could be deleted, for example, even if the original content creator, for some reason, delete them. And you may argue why we need such a feature. And I would like to show you a thing. Do you remember this? Do you remember when, thanks to the developer who had built LeftPad, which is a JavaScript file longs 11 lines. This is the guy. Okay. He was pissed off because some layers argued that other projects that this guy has done were under copyright, so he deleted all his open source project from the internet. And every poor project that depended on it crashed. So this is one of the examples of why we need to make certain things, store certain things in a safe way. And storing with hashes, like we have seen so far, make those things content-addressed files. So once we know the hash, we don't need to bother about where the file is stored, because the peer-to-peer network knows how to find out which nodes contains the file. And from an IPFS point of view, each node, there is no difference between things created on the local computer and added to the local repository, or things pinned from the internet. So just to understand what does it mean to pin, let's say that I connect to an Ubuntu server I have here. I start my IPFS daemon, and I connect also here. Okay, and let's say that I want to pin this guy. So, yes, this is a local Ubuntu server I have on this machine, but the daemon is connecting to the global peer-to-peer network, so it doesn't know about my other local daemon. Okay? Sorry. Not ping. Okay. Very fast. So now, even if I remove from my local storage the content is still available because another node has pinned it. Now, let's think about what does it mean nowadays to deploy a very complex HTML file application in order to support a huge demand. You need to store this application in multiple web servers with caches distributed across the globe, and you have to pay for the bandwidth because the bandwidth is on the server side. So, of course, IPFS is a brand new technology. I mean, it's not has not been around for so many years, but it's functioning, and there is a new initiative called Filecoin from the same company. I don't know if you have heard about it, which is a way to build a sort of blockchain-based incentive network on top of IPFS in order to enable people to participate to the network and being rewarded for it, for storing other people's content. So deploying a big, very big HTML5 application through IPFS means to add the root folder and perhaps deploy a bunch of IPFS node by yourself and pin the content. And if the application is really useful or other people find it useful, they can pin also them too. And in this way, for example, the UI we have seen so far, this one, has been deployed. So this application, deploying application this way means that even if you start up a node on a disconnected network, for some reason, because of you are on an emerging country, or you have problem with connectivity in the place you are, and so, oh my God, oh, we need to go faster, sorry. You are able to start up a node, and all the peers in your disconnected network can use the same content. If the disconnected network is connected to the main network again, you have not to change anything, because it's the content which is the address, not the DNS or the PFS and so on. Okay? Let's move it a bit faster because, sorry. So no more things like this. So just to recap, quickly recap, which are the benefits of static IPFS site deploying. Bandwidth costs are upon the client, not the server. Yes, of course, there is a gateway problem, but you can use IPFS clients on JavaScript as well. The peer-to-peer network is self-organizing. You don't need a service provider to set up complex proxy, clustering, zones, and whatever you want. And also, content is resilient from DNS and IP filtering, and also from deletion, which is not the case for the standard way of doing things. Now, let's move quickly, sorry, to the Ethereum part of the talk and EmbarkJS part of the talk. So this is the standard image from AWS web page. So this is why, and this is how you build a AWS Lambda serverless computing platform. And this is how you can build the same slightly different thing with using different technologies. So instead of using S3 to deploy your static HTML5 application, you can use IPFS. And instead of having an API gateway, you can use smart contracts, which are deployed in a secure way inside a trustless network. Okay? And instead of using Lambda, you can try out the Ethereum network. Because on the Ethereum network, you can run your contracts triggered by the user or an external oracle, an external event of some kind. And they can run inside the Ethereum network, which is in this sense a very incredible big virtual machine made of virtual machine deployed on each node of the network, and eventually store the results of your computation inside the blockchain if you want. And in any case, give back the results to the user. So I don't want to argue about framework-less software design or not. Let's use EmbarkJS as a way to simplify the discovery of such things, the exploration of such a thing. So in order to install EmbarkJS, you need to install before Ethereum, an Ethereum client. Then you can easily install EmbarkJS as an NPM module. Once you have installed EmbarkJS, you can ask EmbarkJS to create a demo project. I will go quickly inside this. This is the documentation about Embark. You can just write Embark demo and you have the full project. And let's run the full project. So let's say, in order to run the project, you have to run, first of all, an IPFS client, if you want to use IPFS as a store, as a data store for your application. And you can have to run, connect to the Ethereum network, or use the simulator inside EmbarkJS, which is very useful to do experimentation without bothering about Ether and other things. So Okay, so here we have our IPFS node already running. Now we have a virtual Ethereum network inside the simulator, and we can run our application. Okay. The nice thing is that when you run EmbarkJS, it presents you a console from which you can see if the services are available. So if I stop, for example, oh my God, okay, I will go faster and faster. So if I stop my IPFS node, it sends it, okay, so I can start it again. And what I can see as a demo, okay, two very simple things. Let's start with, sorry. Okay, oh my God. I need to enable course again. Just a second. Dove sei? Okay. Sorry. I reinstalled the IPFS daemon before the talk in order to start clean. Now it's running. Okay, so I can save something, and it can get me, it can give me back the hash. So the content is stored locally. Then I can see this. And the interesting thing is that the EmbarkJS framework provides you commands to do easily what I've done before on the command line. Okay, and the same goes for the contracts. This is a simple contract you can find inside the demo, which is a simple function that enables you to store a random value inside the blockchain and get the value back. So let's say that we want to store 15, okay, and then get the value back. So what the EmbarkJS framework is doing now is storing inside the Ethereum simulator blockchain the value and get the value back. Okay, sorry guys, I'm a bit late. These are the benefits. You can help build the network and be rewarded for it if you use these kind of technologies. The trust is upon the network, is not upon the provider. And resilience and scalability are built in the network. I don't know if you have any question. We have very few minutes left, but we can manage them. Okay? One question there.
Thank you for the presentation. And
Non funziona? Ah, scusate. Okay.
Okay. First of all, thank you for your presentation. I really liked it. And secondly, you said that Ethereum can compete with Lambda in the current state, right?
Yeah, absolutely.
But if we fast forward a few years when maybe sharding and the Plasma architecture will be deployed to Ethereum, at that point we could have serverless execution of code with virtually unlimited amount of computing resources, right?
Absolutely. I'm a big fan of Ethereum. I know what to mean. The problem is that if we want to compare it now with a enterprise service like AWS Lambda, of course there are problems. Okay, but I think that the right way of doing such a thing is going through peer-to-peer networks like Ethereum. So
yes.
Yes. The answer is yes.
We just have to wait a few years.
We have to wait, and hopefully that we will have such a platform.
Okay, thank you.
Hi. How can we update files on the IPFS network?
That's an interesting question. You can't, and that's a feature. It's not a bug. Okay, if you want to, because in this way, every time you change something, you are deploying to the network the new version, the full new version. That's enabled people who pinned your content before to continue to depend on the version they pinned. So in this sense, it's a feature. Of course, if you want to use it for not storing things that must be preserved, but storing your personal things, for example, you don't bother about other pinning it, I strongly suggest you to use DAT, because DAT was built, let's say, as a tool to substitute Dropbox. So you have your own personal folder, you can change things, and you can synchronize only the changes between nodes. In IPFS, you can't do this, but that's a feature for the IPFS way of doing things. So you have a persistent data storage that can be pinned and can be used across the globe. Yeah. We didn't have the time to show also DAT, but it's another very interesting technology.
Hi. How much is it heavy, this solution? I mean, can I install everything on a Raspberry Pi or maybe my phone?
IPFS, yes. Ethereum node connected to the real network requires, I think, at least 2 gigs of RAM. So it's a bit heavier. But you can build your things upon other nodes. I mean, you have just to you need a client like this, like Embark, to send your contract to the actual network somewhere. But you can run Ethereum on a Raspberry Pi. Yeah, IPFS, yes. It's very, I mean, IPFS, the tool I use here is implemented in Go, so it's very lightweight. You can use it, definitely. Thank you very much.